thick wall cylinder. Uh, Under this session, a little bit uh, large actually. So they will separate to two part. But I will conduct whole sections today. The first part, as per start, we will discuss the stress acting on the symmetrically loaded plane of symmetry. But in this presentation slides, it's not available. I will use the lecture note and I will explain the how to derive the equations, and so that is very important. As previous lectures also, I normally explain the derivations part because it's very important. And the general case of stress in thick wall cylinder. uh, General case means we will derive the equations, general equation, then we will specify that equation for the special cases. Then stress produced by string fit. So there's one of application. So stress produced by string fit. So that we will use that special cases for the application. And optimization of compound cylinder. So that is application optimize. We will use to optimize the application using this theory. So as the first part, we will discuss those things. This is the in this lecture we will use so many equations, and I mean derivation part is very lengthy, but if you understand, there is nothing. So as a very first part, I will describe this theory part using lecture note, because you can see next slide is different thing. So no explanation with the derivation, and so you can see they will directly go to the equations, but so you don't know how to derive this equation without any idea. So if you have lecture note, you can also open that one as hard copy. So I will move to the can you see my slide? I mean screen.
Yes, sir.
I mean screen means not the presentation, the PDF.
No, sir.
No, okay. Now,
Yes, okay.
okay. So if you go through the reduction, you can see this figure and other thing. So you can see there is a symmetrical image. It is symmetric around this axis, BB axis. So we are going to derive the equation stress acting on the symmetrical plane. So normally you need to identify the. So, if they didn't ask the derivation part at the exam, without knowing any theory part, you can application equation if you remember. But this explanation very important to understand the equation. That's the thing. Sometimes you will feel, so what is the importance of knowing these things? If you know the equation, we can directly apply to at the exam and we can get the answer, something like that. But if you get some kind of new questions, I mean, if it is very new, so you need to think with the theory. So that is a very important thing. So that's why I'm explain this one. So you can see this is a this image is symmetric. This figure is symmetric along this BB axis, isn't it? So so you need to identify the symmetric axis anyway. So if you have shape, sometimes if there is no any symmetric axis, you can't apply this theory. So you can see the title also, stress acting on symmetrically loaded plane of symmetry. So first you identify the symmetric axis. So this is the symmetric axis in this figure, and there is a different forces apply on the I will call this is system. So in this system, and you can see the compressive load, tensile load. So even though there is a different type of load, this system is equilibrium. That's mean all the force are neutralized, even though it's applied. Okay, so the vertical resultant force and horizontal resultant force is equal to 0. That is the meaning of equilibrium, statically equilibrium. So then you can separate this image, this system, I mean this image, by this BB axis. You will get the exactly half of the image because it is symmetric around BB axis. So there is a label, some kind of forces here, you can see. So now in this, I will consider left side half. So there is a remaining forces, and so when you separate this system through the BB axis, so what you need to do, you need to introduce the additional forces to the BB plane, because this system was equilibrium with these right hand forces as well. But when we separate this left hand side and right hand side of from the BB axis, so we need to introduce the forces. If it is equilibrium with the horizontal forces, so you need to introduce the additional horizontal force to equilibrium in here, and vertical force as well. So in here, if you apply the horizontal force, it is called stress, nominal stress. And if it is vertical force, you can see it is applied on the surface. So then it is shear stress or shear load and axial load, kind of that. Axial load, tensile load. So you can see here. So I think you understand why we introduce here additional two force in they label as a stress and shear stress. But it is a, if you consider this is load and this is shear load, so I think you understand why we introduce additional two forces in here, because when you separate to balance the system, we need to introduce this one. So they you can see their subscription. This is BB, means the BB on the BB plane. That's why. Okay. And as I told you, in the system, vertical forces, summation of the vertical forces should be equal 0 if it is an equilibrium system, and the horizontal forces also should be, summation of the horizontal forces also should be equal 0. So in that sense, when you get the horizontal forces summations, there will be this sigma BB, so stress on the BB plane, and the shear force, shear stress on the BB plane. So shear force will be addressed with the vertical force, as I told you earlier, and the nominal stress will address with the horizontal force balancing. So you can read this sentence later. So I will already told you these things, and then with this additional, so you can see here sigma. Then see in here they put as a stress. This force applies a stress. So if you convert to this stress to the force, you need to multiply by the area, cross-sectional area. So you can see here the sigma BB and the area as an integral, because you can integrate this area and I mean integrate the BB plane and you can get the area. Okay, that's why there is an integral. You can see this is the force, horizontal force. So towards this right side, and that summation should be equal to 0 definitely. So I mean 0 means if you summation of whole forces in here with the sigma BB as well. So if you put the sigma BB other side, so other summation of other forces, horizontal components, will be equal to this value. Okay. So that is the thing they mention in here. So then what you can do, if you want to find out the at any point, this is sigma bb at the middle, I mean summation of this. So if you want to find out the any point of this surface stress or bending moment, what you can do, because this particular shape has a center. Okay, so assume it is in here. So if the axial load, if it is applied somewhere here, so the center, if the centroid here, it will try to rotate due to this distance. Okay, so you can find out the bending moment at any point using this equation. What you need to do, you need to multiply by the distance. So distance is y. Okay, so integral is come up with this one. So fx time this one fx times y, this is equal to this one, then sigma fx time y, but we are not going to use this fx late, then we will use this notations, and the sigma bb times y, if you convert the sigma bb to force, you need to multiply by area, that is a bending moment. Okay, and that bending moment cannot, definitely there will be bending moment, because we don't know where is the center point here. So if you apply the sigma force value somewhere here, if you apply somewhere here, so if there are any I mean if you deviate from the centroid point, then there will be some bending moment. But if you introduce shear force here, so shear force also with the shear force also, this is trying to rotate. So then it will not balance, because we already introduced the sigma bb. So if you like tau bb, that means shear force, this system not will balance. So sigma b, I mean shear force will be 0. Cannot, because bending moment will be cancelled out. Okay. There will be bending moment, you can see here. If you separate these two, there is a bending moment due to these forces. So if you introduce tau bb also, shear stress also with this kind of function, it is a kind of trouble to balance the system. And additionally, the shear force normally apply on the surface, not the perpendicular surface. So we can get as a sigma I mean shear stress equal to 0. So did you understand that part until that point? Any questions? Because I'm going to give the very strong statement here. So if you understand that, only you can get an idea about that. Anyone? If you don't understand, tell me. I can't hear you. If you mute your mic, I can't hear. Are you guys there? Hello.
Yes, sir.
Okay. So others are not here. I don't know. They will log into this lecture and they will not listen to something. I don't know. Anyway, so with this statement, you can easily get the idea. So the selected plane, that means BB plane, this plane, it is the principal plane. Okay. If you remember that, what is the importance of the principal plane, that means there is no shear stress. So last lecture also I mentioned, if you draw the Morse circle, the principal stresses given given on the x-axis, that means the shear stress will be equal to 0 at that plane. Okay.
Sir,
Yeah.
excuse me, sir. Now, in this component, there are components of forces to the vertical direction, right?
Yeah. Sorry, I didn't get what you asked.
For example, the F in the F3, the force F3. So
These forces.
yeah, F1 or F3.
Yeah. Okay.
There's a component along the vertical direction, right?
Yeah. Vertical direction.
So why the shear stress cannot be applied to that surface?
Okay. I will draw here. I think I got what you're asking. So if it is not what I'm explaining, tell me. Okay. So you can. So you have F1 here. So you can get the horizontal component of this F1 and vertical component. Am I right? Assume this is vertical component. Okay. And F3, this is vertical component. This is horizontal component. F2, this is horizontal component. So assume this is in x-axis. Okay. So we don't have any y component in here. Okay. And if you separate this system at the BB plane, okay, this is BB plane. If you separate, there is nothing happened to the vertical forces. Can you see here? So these vertical forces apply on this side. Okay, these vertical forces apply on this side. Okay, vertical forces. These forces apply on this side. These forces apply on this side. If you get the vertical and horizontal component of all the forces, the vertical forces apply on this side and vertical forces apply on this side is independent, not dependent. But horizontal force, it is dependent because we select the vertical plane. That's why. If you select the horizontal plane, same results will be happen. So assume your symmetrical plane, this one, this is not symmetric, assume. So you can't get the independent results for the S component. Okay. So S components are dependent, but y in here y components are independent. Okay. So if you get this part, the y component will be cancelled out with these forces. We don't worry about the y component then. That's why it is going to be 0. Are we clear?
Yes, sir. Yeah.
S component we cannot be cancelled out because there is a plane. Okay.
Yeah.
I hope you understand.
Yes, sir.
Then so with that theory, that explanation we can easily grab now, because we already know at the principal plane there was no any shear stress. Shear stress is going to be 0, or you can call it absence of shear stress. So if it is shear stress is 0, that plane is principal plane. The stress principally stresses. Are we clear? So that means the symmetrical plane, it will be principal plane. Are we clear? So you can see with this statement, we conclude therefore that for a body load symmetrically about a plane of symmetry, the plane of symmetry is free from shear stress and hence is the principal plane. Are we clear? So that so you should know what is the meaning of principal stress and principal plane. Okay. So I explained this one with the second lecture, I think, the very beginning of semester. And so now we know load apply on the symmetrical plane, and so don't ask then at the symmetric plane why we don't want to introduce shear stress. Now we know what's the reason. And yes, in your presentation, next slide is we will derive the thick wall cylinder equations. So I will use the lecture note because there is only this image without any explanation. So I will use and I will until the derivation of the equation I will use this lecture note. And you can see here the cross section of the thick wall cylinder. So you can see the small segment selected on the thick wall. So this is called MN plane. This is M1N1 plane. That means the kind of tangential surfaces or circumferential surfaces. Okay. So covered by these two surfaces, and this is a small segment we select. We will use the theory for this segment. Okay, and that is valid for anywhere of the cylinder. Are we clear? And it is externally pressurized. It is as a compressive load. So this is also compressive load. So internally also pressurized, and it will be rotate. Okay, we call it externally and internally pressurized and rotating cylinder. So this is the this is address whole thing, but later on we will call non-rotating cylinder, rotating cylinder, only externally pressurized, only internally pressurized, and special cases we can describe, but this is the general case. And selected angle also delta angle d theta, and the selected segment has a length dr. Okay, so if you want to find out the length of this arc, you need to use the equation of this r theta. Theta should be radian. Okay, so you can find out the length of this arc, and this is dr. This is also dr. Okay, so here center to this MN plane radius is r. This is dr. Then the M1N1 radius is r plus dr. Okay, so I'll just introduce the labeling system because we should know how to what are the notations when you derive the equation. That's why. So then if it is equilibrium segment, I mean small element, so we can use the force equilibrium force balancing equations. Okay. And if it is rotating, if the segment is rotating, there is a centrifugal force. Okay, so I hope you know the equation of the if we apply the F load here, equation of that. What is the equation? M F equals
mr omega squared
omega square r.
r.
Omega means the rotating speed.
Rotational speed.
So you can see when you read this sentence, so in this part, in here, explain that centrifugal force. Okay, so you can see here this this is the m r omega square. So sometimes you will feel there is no any m, so they will find out m with this volume. Okay, so you can find out this small segment volume using the given data. So in here r d theta, as I told you, in here d theta, angle is d theta. So this is r. So you can find out the length of arc, that is r d theta. R d theta. Okay, r d theta, that is the arc length, and dr, that is this length. Okay, are we clear? This is dr. So you know now when you multiply by r d theta by dr, that is the cross-sectional area. And if you multiply by, so this is a cross section, so you will select the so there is a length of this cylinder. Assume this is length L. So you will select the small segment of this. This is dl. So length of this segment. Okay, this is into the slide, into the this plane, inside to the plane. Okay, this is dl. So there is the volume there. So we know volume. So if you multiply by density, this is the mass. it clear? So omega squared R. So this is centrifugal force. Then, so we will select this small segment, and this is FB. We already know that it's that value. And then we will introduce other forces apply on that small segment. So this is sigma R, nominal stress at this plane. And outer surface, this is inner surface, this is outer surface of this segment, okay, or not the cylinder outer surface, this one. So we will select this segment as this segment outer surface, this one. So this is this side sigma R, speed is sigma R. If it is a balanced system, it should be sigma R as well in this side, and plus due to this distance, there is a you can see d sigma R differentiate by R with the radius, that shear nominal stress will be changed. So that's why we will get the differentiate here and multiply by dr. Okay, so I think in the mathematics you learn this thing. Okay, I'm going to explain this one, and then these are the radial forces. So then we need to consider the tangential force. We will consider exactly this point, okay, center point of this element. So if you consider the center point, so this is I'm sorry, this is kind of curve shape, not the exactly this kind of rectangle. This is arc shape. So if you draw the straight line through this point, center point, so this plane little bit deviate. So if you draw the perpendicular axis, line through this axis, it will be like this. Okay, and if you draw the perpendicular line belong to this plane, it will be like this. So if you want to get the tangential stress, we call this side tangential stress, and the out of the plane longitudinal stress, we call like that. So tangential or circumferential stress we can find out using sigma t, but we can get the sigma t of this plane, and we need to get the component, this component, okay, get as this is x-axis, this is y-axis. So y component, not the x component. So y component we can get using this equation, because if it is d theta, this is d theta, so this is half of the d theta, and that this angle also half of d theta. So then you can get the component of the sigma t, and same thing this side also, sigma t sine d theta divided by 2. So I think it's clear. I will erase this thing. So I'm going to read this, and I already explained. And then this is the force balance. Okay, so radial forces in this direction forces. So in towards this directions there is a sigma r. This is area. Okay, this part explain the area. Sigma r, this one. So you need to find out the area of this surface. That is the length is r d theta, and there's a depth, it is dl. So this is the area of this plane. So if you multiply by sigma r, this is the load applied on this surface. And in here we consider the radial forces to this direction, that's why it is positive, and this one is negative. This is the stress multiplied by this surface area, that is r plus dr, that is the radius. You can see r plus dr multiplied by d theta, that is the arc length, and multiplied by dl, that is the area. Okay, and then you can see here the this sigma t, that means tangential stress, also get this if you assume this is x-axis, so s component, so two component will be here, one component from this one, another one inside, so both are equal. So 2 sigma t sine d theta divided by 2, this is the area. So this length is dr and depth is dl, and it should be equal to the centrifugal force. You already find out this one. Or if you put this one as a minus and put the equal mark equals 0. So this is if it is minus. If you put this one to other side from the equal sign, then it is plus. So this is the equation. So this is very important equation now. So then what we are going to do, we are going to simplify this equation. So we can divide this equation by, you can see there is so many r, d, theta, dl and dr. So you can divide whole equation by this part, r, dr, d, theta, dl. And you know this is this angle is a small angle. So I think in your mathematics knowledge, you already know, if you get the sine 1 and 1, it is not, I mean, if you get the small angle, the sine value also equal to the numerical value of inside of the sine. So you can put the sine d theta divided by 2. You can see in this, there is a sine d theta divided by 2. That part as a d theta divided by 2. That is mathematical knowledge. So for the small angle only. So then we can simplify. If you divide this one by r, dr, d theta, dl, what happened? R, d theta, dl will be cut off and only remain dr. Only remain dr. And then in here, you can expand this one and or you can cut off here d theta, dl, and there is only r, dr. Then r will be cut off due to expansion in this. So sigma r divided by dr. So this sigma r plus 1 will be cut off to this one. So likewise, you can expand this one. Try out at home, and you will simplify until this point. You will surprise. So you can see even though there is a lengthy equation, it will simplify until this point. So then what you need to do, in here you can see d sigma r divided by r in this one. So this one, this one is where this is d sigma, that is the drop of the radial stress. That is very small amount. So when we compare other values, this can be cut off. Okay? This is much smaller. So you can see in this equation that term will be removed because it is a very small value, and multiply by r. Whole equation multiply by r. So same equation, we can cut off this one. This approximately equal to 0. So then when you multiply by r, you can end up with this equation. So this is the equation we will use to derive the equations later. And so until this point, we calculate the stresses. With the stress, we using force balance, we calculate the stresses to calculate the one of the equations. So we already got the one equation. Now we are going to analyze the strain. Okay. So strain. So I'm not going to read again this one. So I will summarize what is the thing there. So you can see if you apply the stresses, the small segment can be expand or shrink. So assume this is expand. So this particular surface can be somewhere here. This surface can be somewhere here. So you can see here. So so difficult to understand if it is overlapping. That's why it's separate. Sometimes the inner surface can be somewhere here. How does it? So then you cannot easily understand. It's very difficult to figure it out, the labeling and other things. So that's why they separate this one. Okay. So then you can see this is the expansion with the additional forces. When it rotates also, the surface will be try to move to the radial direction, okay, outward to the center. So this is the initial radius. So with the force apply on this one and rotation, this small segment will be move to the outward to the center. So then you can see this is the deflection. So not deflection, this is the displacement. This is displacement. So normally we label u with the strain energy, but in here it is not a strain energy. Okay, so don't confuse that notation. This is u means the displacement. Like you normally put the e or x for the displacement. In here they use u. Okay. So r plus u, that is the displacement of the inner surface. Then outer surface displacement, it will be this one, u plus du by dr times dr. Like the stress, you calculate the inner surface stress. When we are going to outer surface, you will use this kind of mathematical equation. Okay. So that is the outer surface displacement. So then you can find out the radial strain and tangential strain separately. Okay. Tangential circumferential direction strain. So in here, if you want to find out the radial strain towards this direction strain, so you normally it is labeled as a epsilon r, radial direction strain. So strain is displacement divided by initial length. So you can see here displacement is du by dr times dr by dr. So in here du by dr, so you can see displacement, this one, du by dr. Okay, that is the displacement. That's the radial direction. So you can calculate, you can get this displacement by du by dr, and circumferential directions strain. It is this direction. So when you calculate this, you need to find the arc length, initial arc length, this one. It is r d theta, and this arc length r plus u d theta. That is a radius r plus u. So you need to get the difference between these two arc lengths. So r plus u d theta minus r d theta. That is the expansion of the circumference. Then divide by the initial circumference. So then when you simplify this one, you can see d theta will be cut off, and r plus u minus r, then r will be cut off, u divided by r. So this is the tangential or circumferential strain. And you know the biaxial system, we discussed this one in the lecture number 2. Okay, so I hope you know we apply the Hooke's law in here, and we find out the we call this is sigma x and sigma y. Okay, at that time we will calculate the sigma x and sigma y with the sigma epsilon x and epsilon y. Okay, so I'm not going to explain this equation because you already know how to derive this equation and other things. I hope you remember. So then what we are going to do, we already calculate the equation for the sigma r and sigma t, and now we know the another relation with the sigma r and sigma t, that means radial stress and tangential stress. So what we can do, we know sigma epsilon r and epsilon t as well. separately. So we can substitute in here sigma epsilon Rn is epsilon T into this equation, and then you will get the equation for the sigma R and sigma T. That equation you can substitute in here, sigma T and sigma. And in here sigma R you need to differentiate with respect to R, then you substitute here. Yeah. So you have sigma R and sigma T here. So after substituting epsilon R and epsilon T from here, so epsilon R is du by dr in here, and u divided by R is the tangential strain. Then you can, when you substitute in this equation, sigma R divided by dr, so you need to differentiate with respect to R that particular equations and substitute to that equation. So this is the format of that equation. Okay. Then we can simplify that equation with expanding, and some of the thing will be cut off. And this is the equation. You can see when you, this is the this is the thing introduced in here. When we simplify this equation, so I will tell what they did. First, we can multiply by this one and divide by e, then all the term will be cut off in here. It will come to here. So 1 minus nu e square divided by e we will use to multiply the whole equation. Then you can cut off the things, we'll cut the plus and minus thing, and the remaining part will simplify and then multiply by minus. You can see in here the omega terms, that one is plus here because in here minus. So that means a whole equation you should multiply by minus, then somewhere here this one only will be minus. So this is the equation. This is second order differential equation. So last lecture also I told you, if we have second order differential equation, so the mathematics knowledge we should use to solve this differential equation. So you can see there is a d squared u divided by dr squared plus du by dr and u also here. So this is the normal second order differential equation. So when you get the solution for that equation, it will be like this. I'm not going to explain, that is the mathematics thing. So this is the equation. So if you have mathematics knowledge very well, so you can get this equation. So in here C1 and C2 are constant. So I told you last time also, if you have constants, so you are the person introduced that C1 and C2, you need to find out. So when you are going to find out that C1 and C2, so we know the u value now, the function of u. U means the strain, so displacement. So we know the displacement now. So what we can do, we can introduce that displacement value, u value. So you have equation in here. So with the epsilon r and epsilon t, it is epsilon r is u differentiate with respect to r. That means this equation you need to differentiate with respect to r, and it is epsilon r. That one you can substitute in here, and epsilon t, that is u divided by r. So this is u. You can divide this equation by r and substitute to epsilon t, and you will get the equation for the sigma r and sigma t. You can see sigma r and sigma t. Then you can see here an important thing in here, e and nu and c1, all the things are constant. In here also all the things are constant. In here density also constant, nu constant, material constants, omega the rotating speed, if it is constant, in that case, it is also constant, but it can be vary according to the rotating speed. But in here, parameter is r, the function of r. So with the radius will be changed along the radial direction. So then this is function of r. So you can see that this equation we can note down like this. So this whole part can be taken as a one constant, because if you know the material constants and this constant value, so we can generally we call this is one of the constant value. This is also constant value, but there is r square. So k2, that part, this part calls k2 divided by r square minus, you can see if it is omega constant in that particular case, so this one part will be constant, so r square. So these two equations we can rewrite like this. So now we need to find out the C1 and C2. Still we didn't find out C1 and C2. So C1 and C2, when you're going to find out, we need to use boundary condition. So we already know two boundary conditions. What are the two boundary conditions? At the surface of the cylinder, the external pressure is P0. Internal surface, the internal pressure is Pl. So then so we derive this equation for the small segment of the on the wall of the thick wall cylinder. Now we know, if we consider the outer surface of a cylinder, that is r equals r naught, because the r naught outer surface radius. Inner surface, it is r, right? So these are the boundary conditions. The minus sign, as I told you earlier, it is meaning compressive stress. Okay. So that is the case. I think I can continue from here using that presentation. So I will go to the presentation. I will stop the sharing this PDF. Yeah, okay. So this thing I already explained. This is tangential radial. This is a small segment considered. This is the equation with the C1 and C2. So now we are going to find out the C1 and C2 with the boundary condition. These are the boundary condition. Yeah. So if it is non-rotating cylinder, so since here we will consider non-rotating cylinder, that means omega equals 0. If it is omega equals 0, what happens? This term will be eliminated. So only remain these two. Sigma r, that means radial stress, only belongs to this part, and tangential stress only belongs to this part. So this will be 0. So now if you consider non-rotating cylinder, then boundary condition, the stress minus pi. So in here you can see the boundary condition applied, because r equals ri now. Then the stress will be pi, and the outer surface r equals r naught, and is p naught stress. So now we have two equations. We have two unknowns. So we can solve this equation and find out the C1 and C2. So these are C1 and C2 answers for the constant. Okay. Sometimes you will surprise even though these are the constant, there is a radius. But don't worry, because these are not the variable. R naught and Ri is the constant. It is the boundaries. That means R naught and Ri, those are constant for the particular case. Outer surface radius, it is not going to change. Inner surface radius is not going to change. So this C1 and C2 are constant. Pi and P naught also, in the particular case, it is constant. The pressure or stress will vary along the radial direction, not the outer surface and inner surface. That's why we call the boundary condition. So then what we are going to do, we have the equation with the C1 and C2. So we will substitute C1 and C2 to that equation with these terms. So then this equation will be like this. Sigma R, that means radial stress, will be like this after substituting C1 and C2. So sometimes you will surprise because there was a E divided by 2 1 minus nu. So you can see in here 1 plus nu divided by E. So that's why it will be cut off. So there is no any material constant nu or elastic modulus. So this is tangential stress. Another important thing in here, you can see all no variable, everything is constant. Outer surface radius, inner radius. This is the only variable. This R. This is the R vary along the radial directions. This is tangential stress. You can see here also all things constant for the particular case. This is the only thing vary. So you can see everywhere R, but these R has some values for the particular case. So now this is the outer radius and inner radius are all together in this equations, two equations. What we are going to do, we are going to rearrange this equation. So simple manner. So this is the rearrangement. Same equation. If you expand this these two, you will get same thing. So this is radial stress. This is tangential stress. You can see. So you can't easily see the variable parameter in here, this equation, but in here you can easily see. This is the thing. Other things are constant. This one also constant. So these two are variable. This is tangential one, same thing. You can easily keep in mind also this equation rather than this one. This is very difficult to keep in mind. Okay. So this is the finalized equations for the radial stress and tangential stress for the non-rotating cylinder. Don't this is not a general case actually. So this is non-rotating. So only externally and internally pressurized. So this is the internally pressurized part. This is our externally pressurized part. Special cases. Before that, do you have any questions until this point? So derivation, when we derive the equation, expect that mathematical thing. I mean, how to get the second order differential equation answer. Like that things, expect that things. So do you understand everything until this point?
Yes, sir.
Others?
Yes, sir.
Okay. Special cases. So we already derived down non-rotating cylinder equation. So now we are going to discuss the special cases with the non-rotating cylinder. First one, internally pressurized. That means there is external pressure, non-pressure from the external. So external pressure is equal 0. And second one, external pressurized non-rotating cylinder. That means in PI equals 0. Internal pressure equals 0. And then externally pressurized non-rotating solid cylinder. So if there is internal radius, that means it is hollow cylinder. So that means in here Ri equals 0. That is solid cylinder. These two belongs to hollow cylinders. This is solid cylinder. So we will discuss some special thing what we discussed earlier with the stress consideration lecture. At that time I told you hollow cylinder and solid cylinder stress difference. So I told you at that time we will discuss this one later. So today we will discuss that one also. If you remember that equations, you will remind that. So first, internally pressurized non-rotating cylinder. So in that case, as I told you, P naught equals 0. then this is the general case for the non-rotating cylinder. So if it is this is a tangential stress, so general case. So if it is internally pressurized only, the P naught will be equal 0. That means these two terms will be cancelled out. So this is the only remaining part. Okay. The non-rotating internally pressurized one, you can use this two equation. So then we can use the boundary condition and find out the stresses at the boundaries. So if it is R equals Ri, what happened? And R equals R naught, this term will be 1. So sigma R will be 0. And R, if it is R equals R naught, in here it will be 1. So it is 2. Then 2 pi Ri squared and R naught is squared minus Ri squared. And if it is Ri, these terms not eliminate, but if it is Ri, again this one has also value. So in here the radial stresses will be absent when R equals R naught. That is the meaning of here. So you can see here sigma R at Ri, that means inner surface. It is Pi, we already know. And sigma R at R naught, it is equal 0. So you can substitute that equation and get that value. So if it is Ri, what happened? Ri squared, when you get the common denominator, so this will be Ri squared minus R naught squared, and this will be Ri squared. Ri squared will be cut off, and when you get the minus sign outside, this will be R naught squared minus Ri squared. This will be cut off, so minus Pi. So likewise. So I'm not going to in detail explain this one. So then second equation we can use to calculate the tangential stresses at the inner surface. So this one. So as I told you, this is the answer. So you can simplify if you want that equation. And then the outer surface tangential stress. This is the value. So now we can plot that one. Okay. So this is the cylinder, inner surface and outer surface. If you consider the center point of the cylinder is the origin of the axis. So toward this direction, assume this is x direction, towards the radial direction, this x directions, and this is assume the perpendicular to that axis. So you can see the variation of the tangential stress towards to that radial directions and tangential stresses also. So with this equation, you can see radial stresses always it will be minus. Always it will be minus. You can see here at the surface it will be 0. Outer surface, inner surface it has some value. It is it will be minus P as well. You can see. Then tangential stress at the surface it has a value. You know already values we already find out. This one, and this is inner surface value. It has some value. And if you go radius, okay, in here radius is if you consider the outside of the cylinder, there is some both line will be trying to symmetrical around this axis. It has some value. So you can see with the equation you can get this value also. So when that R goes to infinite, you will get this value, the constant value. what you need to do, you can use these two equations and put the r equal to infinite, then you can see what happened. This will be 0, this will be 0, then this is the part remain. It is a constant, so it's called kt. So this is the variation of the tangential stress and radial stress on the thick wall. Then thick wall was thin wall. So we should know what is the margin of thick wall and thin wall, because we don't know that. Okay, can we call the thin wall for this cylinder? So assume this is the thickness of the cylinder. So can we call the thin wall or thick wall? We don't know. Or if it is like this thickness, can we call the thick wall or thin wall? We don't know. So if it is thin wall, it should be like this or something like that. We don't know. So we should know the margin of the thick wall and thin wall. So let's see. So when we consider the thick wall and thin wall, thick wall one, we don't want too much worry, because the maximum stress for the thick wall in here, thick wall cylinder, maximum stress. So I want to show you in here, the maximum stress belong to this one, okay, sigma t, not the radial stress. Okay? So tangential stress will be maximum at the inner surface in this case. So we will consider this one. Okay, so this equation. Then thin wall, this equation will be simplified until this point. So I will tell how it will be happen. So what you can do, you can put the Ri. So if it is thin wall, that means there is no thickness. So R naught and Ri should be equal. Okay. So then what happened? This term will be goes to 0. It cannot be happen. If it is Ri and R naught equal, this term will be 0. But there is a small thickness. So we are not going to substitute Ri equals R naught here, or R naught equals Ri here. This is keep remaining as same as it is. And in here also we will substitute R naught as Ri. Okay. So then you can easily see what happened. Then R naught equals Ri, this 2Ri squared, and you can expand this one as R naught minus Ri times R naught plus Ri. That one also, if you have, okay, I will note down here, R naught minus Ri, expand in this part, R naught plus Ri. In here also, R naught plus Ri part, you can put the R naught as Ri. Then this will be 2 Ri. So in here 2Ri squared. So 2 to 2 will be cancelled out. R naught squared and so Ri squared and Ri. From that only remaining Ri. So you can see it will simplify until this point. Okay. So now don't ask why we are not going to substitute here also Ri. Then it will be 0. Okay. So don't think too much about that thing. So only keep this one as a constant, the difference. So now we have two equations. What we can do, we are going to try out the margin of the thick wall and thin wall. Okay? Keep it in mind. So we can get the ratio between these two equations. Pi will be cut off, and okay, I'm going to explain so you can get this equation. Now R naught and Ri, those are constant values. Okay, so you can use R naught to divide whole equation, all the terms. You can divide R naught squared, R naught squared, R naught squared, R naught squared, like that. So this will be 1. This is R naught Ri divided by R naught squared. and this will be Ri divided by R naught. This will be Ri divided by R naught square. So then we will consider Ri divided by R naught. As I told you, Ri and R naught is a constant for the particular case. So you can call it a constant, ratio also constant. Then this equation will be simplified like this. So this is the equation. Now we can plot with this we know this ratio now. If you know this ratio, Ri divided by R naught, that is K. So stress ratio, so variation you can see. So that R naught, if it is equal to Ri, or Ri equals R naught, the ratio will be equal 1. Definitely it is thin wall. But we should know where is the boundary line of the thick wall and thin wall. You can see in here until 0.9, that ratio 0.9, that means the ratio between the Ri and R naught, if it is 0.9, it is very close to the stress ratio as a 1. If it is stress ratio, if it is equal 1, it is thin wall. But after 0.9, you can see little deviation, and the ratio, if it is increased much higher, you can see R naught is, if it is very less rather than R naught, that means there is a very high thickness. So then we cannot consider as a thin wall, it's a thick wall. Stress ratio variation is very high, you can see. In here, stress variation is very high. So this is the statement. The pressure vessel is considered a thin wall if its radius R is larger than 10 times its wall thickness T. If it wall thickness means R naught Ri difference. So that thickness, if you consider that thickness, and if you multiply by 10, that thickness, if it is less than R, you can call it is thin wall. So very simply we can say, using that graph, this graph, if K value, if it is higher than 0.9, that means it is very close to the 10T, that's why. So then it is thin wall. Are we clear about that? Any questions?
Yes, sir.
Okay. Then externally pressurized non-rotating cylinder. Now we already discussed the internally pressurized non-rotating cylinder. In this case, Pi equals 0, not P naught. Pi equals 0. So these are the two general equation for the non-rotating cylinder. So if it is Pi equals 0, this is the equation. So now again we can find out the boundary conditions using boundary conditions and values. So what you need to do, substitute Ri and R naught here, Ri and R naught here, then you will get at the inner surface and the outer surface radial and tangential stresses. So I'm going to explain now. You already know how to get that values. So those are the values. Now we can plot the variations. So you can see in this case the radial stress, it is equal at the inner surface. So it was earlier 0, radial stress 0 was the outer surface. Now it is inner surface because it is externally pressurized. Earlier one is internally pressurized. So if it is externally pressurized, inner surface radial stress should be equal to 0, and outer surface radial stress, it is equal to minus P naught, because it is compression. And then tangential one, it has values, but it is a switch. Earlier it was separate. R naught has a 2 P naught, R naught square, like that. Now switch between these two. And then you can see here, in here also maximum stress as a value, as a magnitude, maximum stress given by tangential stress. It is also available at the inner surface. You can see in the earlier case also, the tangential stress is maximized at the inner surface. It was the maximum stress of the system also. You can see. So I'm not going to explain now this variation, how to draw that and other things. Now you know how to draw the curves. Then externally pressurized non-rotating solid cylinder. In that case, Ri equal to 0. It is solid cylinder. So externally pressurized one. So we don't want to use the general equation now, because Pi terms will be 0, because externally pressurized one mean internal pressure is equal to 0. And this is the equation for the external pressurized non-rotating cylinder. If it is solid cylinder, what happened? Ri also going to be 0. Then this one and this one also going to be 0. So then what happened to the equation? Let's see. This is the thing. So this is tangential one. So Ri, if it is equal to 0, this one also it is equal to 0. This terms will be 0. Then R naught will be cut off. So then it's minus P naught minus. That means externally pressurized non-rotating solid cylinder, sigma R and sigma T, that means tangential and radial stresses are equal. It is equal to minus P naught as well. It is equal to externally pressurized pressure. So this is the general equation for the sigma R and sigma T. So we already derived these two equations, rotating cylinder equations. So you just know this this equation. So without these three terms, you know the equation. But you can see here there are additional things. So in this level, we are not going to explain that much of explanation. But this is a general equation for the radial and tangential stresses. So these equation will be provided at the exam. But you don't worry about the, keep in mind that the equation. If it is a open book exam, maybe you can check your lecture note. But if it is a closed book, definitely equation will be provided. So don't think if you will get this kind of equation. No? So you need to derive this equation using this long equation. No? They will only provide these two equations. If they provide that particular specified equation, it's better. But if they didn't provide, if you only get these two equations, you need to derive that equation using those two equations. If it is non-rotating cylinder, so these two terms will become. So if it is P naught 0, so you can likewise you can find out the exact equation for the special cases. So as I told you, we just only discuss non-rotating cylinder, externally and internally pressurized. Effect of pressure vessel stresses. I already explained these things. The normally maximum stress given by the tangential stress, and so normally we will use a thick wall cylinder for the pipe. You know, the oil will transferred by the pipe. There is we call it thick wall cylinders. Gas transformation to another point using pipe. So there is internal pressure as well external pressure. So and it is non-rotating, so you can use this theory. And normally in here you can see the one statement here there. So they will doing the inspection inner surface after any earthquake or after anything happens, they will check the stress at the inner surface, because in this whole cases tangential stress was maximize at the inner surface. So if it is exceed the yield stress, definitely crack will be initiated at the inner surface. So you can't, no one can see the crack outer surface until it propagates. So because the inner surface is at a high stress. So if you're waiting until the appearance of the crack, it will be huge damage. So normally, if you want to early detect the failures, what we need to do, check the stress of the internal surface. I mean, internal internal radius circumference. You need to check the stresses. Then you can avoid the catastrophic failure. So there's a thing they explain here. Because yielding will govern by tangential stress in here. Okay, and yeah, then shrink width. There is a theory. Normally, we can fix. I will draw here, and then you can rather than explain that one. So if we have a cylinder like this, thick wall cylinder like this, you can fit another cylinder onto this cylinder. There is a reason for that. Still you don't know what is the reason. So when we explain, when I explain to you, you will grab what is the reason for that, and I will summarize later also what is the reason for this one. So without using one single cylinder like this, assume this thickness and this thickness are equal, two cylinder thickness and this one single cylinder thickness is equal. Then instead using one thick cylinder, so normally we will use compound cylinder. This is called compound cylinder. Combining two cylinders together. So at that time, there is an interface between these two cylinders. So when they are joined these two cylinders, they will use a different kind of technique. Sometimes they will heat up the inner cylinder and fit to the outer cylinder. Sometimes they will cool the outer cylinder and feed to the inner cylinder. Different kind of techniques are there. Okay, so because this is shrink width. Okay, so when it's feed to the other cylinder, so inner cylinder and outer cylinder feed together, there are also pressure. We call it shrink width pressure. Shrink width pressure. Okay, this interface, and there is some kind of displacement as well. So we will later on discuss about that displacement also. So we call interference. Okay, so interference, that is deflection we call interference. Interference, deflection, displacement we will calculate later using the theory what we are going to learn later. So as I told you, there is a J and K, two cylinders, and initially we will consider those two cylinders are made by different two material. That means two material has different elastic modulus, different new position ratio, different position ratio, likewise. But later on, we will consider that two cylinder has the same made by same material. Then that elastic module of the K cylinder and J cylinder, it will be equal. So yeah, in here they didn't explain the derivation. I will again move to the lecture note, because without that explanation you don't know how to get the exact idea about the cylinder. So can you see my PDF now? PDF.
Yes, sir.
Okay. So we are here. Yeah, you can see here. So in here also we will consider the displacement, as I told you. So displacement we call, radial displacement we call u. Well, also we use that notation. So then that u, this is taken by the equation we derived early, equation number 20 in here, using these two equations. Using these two equations, substitute the C1 and C2 and get the equations belong to a particular case. So if you know the C1 and C2, you can substitute there was a equation for the U. So that C1 and C2 you already know, so you can substitute C1 and C2 that function of U, then you will get this kind of equation. Hope you remember, we already using second order differential equation, we find out the U function of the U. Now there was two constants C1 and C2, so we already know the C1 and C2, so you can substitute that equation and get the U value. And then a radial displacement of the J cylinder. J cylinder meaning outer cylinder. So the outer cylinder, assume in this cylinder doesn't have external pressure, okay, only internally pressurized due to this K. This J is not pressurized from externally. Due to this K on this surface, there is a pressure, okay. So it is only internally pressured due to K. Then that contact pressure, it is simple P kind of notation. Then the radial displacement of a J cylinder, we can get the equation like this. So this is, sometime you will be confused how we can get that equation or something like that, because you can use the equation of the displacement, radial displacement U value like this, and you can substitute here Pi, there is a Pi value, and P naught equals 0, then you will end up like this equation. In here B and C, sometimes you will see there is no any B and C. In here B and C means the boundary point, okay. So you know R naught of J value is C, and B means Ri. You can see B and C here, and new J and EJ, those things come with this. Just new substitute with the new J, and E substitute with the EJ, because we consider those two cylinder made by different two material. That's why. So Pi value equal to contact pressure at this point, internal pressure. So you can use this equation, just substitute all the things, and you will simplify like this equation. And same thing you can use for the K cylinder, internal cylinder. Thing is, it is not the internally pressurized, it is externally pressurized due to K. Then in here Pi0, P naught has a value, it is a contact pressure, simple P. And again E and nu, it is belong to the K cylinder material constant, okay. So that's why E K and nu K. And boundary condition in here, not the B and C, it is A and B. Ri is A, R naught is B. That's why here A and B you can see. So then if there is any displacement of this interface of these two cylinder, there should be a difference between these two. That is the main thing. So you can get the difference between these two, because due to this K, J will be going to expand. Due to this J, K is trying to shrink. So if you get the difference between these displacement, you will get the actual radial interference. So we call that radial interference label as a delta. You can see here, yeah, delta is the radial interference. So then what you need to do, you have two equations, you get the difference between these two. So when you get the difference in here minus, that's why in here plus. So it is equal to delta. And as I told you, so if you made those two cylinder in using same material, that EJ and EK equals and new J and new K equals. So those things you can simplify. So you using that equation, substituting these two as a EJ and EK as a E, new K and new J as a new, then you will get this equation. This is the so you can see in here the contact pressure. You can the surface between the interference between the two cylinder contact pressure is given by this equation. And keep in mind this radial interference you will calculate for the one single side. So this will happen to others opposite side as well. So as a diametric wise, it should be 2 delta. Okay. So that's why in here you can see statement the half of the diametrical impedance. So if there's a expansion, so you need to get multiplied by 2 delta. 2. It should be 2 delta. So in the question, if you get like this cylinder and if it is expand like this, so if you get the 2 diameter, so then so assume this is outer surface, not mentioned down. Okay, so it is explained like that. So if you're going to get the interference, don't get the difference between the diameters. You need to get the difference and divide by 2, something like that. Just for understanding, I explain here. So then you can rearrange different manner that equations. So I will move to the slide now. Can you see my presentation?
Yes, sir.
Okay. Yeah, so I already explained this equation now. So this is the contact pressure at the sink pit. Yeah, and with this example you will easily understand how we can deal with that equation. So determine the stress in the build-up steel cylinder subject to an internal pressure PI of 200 megapascal. ABC is given and the sinkage delta is 0.13 millimeter. So that means they provide the delta value. So you need to find out the contact pressure P. So yeah, superimposed single pressure, yes. So this is the this is the equation. Directly you can use this equation. E values provide, delta values provide, and A, B, C is given. So just substitute and find out the interference pressure or contact pressure. The tangential stress produced by this pressure is the inner cylinder. Then you can this is contact pressure. So tangential stress produced by this pressure, you need to calculate using the equations belong to tangential stress and radial stress. So then for the outer cylinder, sorry, this is inner cylinder. So inner cylinder will try to sink due to external cylinder. So then it is kind of externally pressurized cylinder. So then you need to find out the externally pressurized equation, non-rotating equation. So they substitute the values, the radius R naught and Ri, A and B, and this is the parameter. So you will get the equation. So when you do the calculation using this kind of equations, get the general equation. So don't substitute R value in here. So if they ask okay, given value is R value is given, so you need to find out the pressure tangential or radial stress at that radius. But don't substitute here, just simplify like this, that equation. And if they ask next step another radius, you need to again do the calculation at the beginning. So if radius variation only, so you substitute here and get the values directly using this equation. So in that case, this is your equation for the that special equation. So that equations not changed, so you can use this equation as a general equation for that particular case. So this equation valid for the 100 to 150 millimeter, because this is valid for the only internal cylinder. You can see A is 100, B is 150. So it is valid for the internal cylinder. And then you can find out the tangential or tangential stress for the oh yeah, you can see here when R equals A, you can find out substituting here. A value is 100 and B value is 150. You can substitute and find out. If they ask when R value is 120, you substitute and find out. If they ask to plot the curve of the stress variation, then you can easily draw that using different kind of point on the curve. Then tangential stress produced by this pressure in the outer cylinder. So outer cylinder will be trying to expand due to inner cylinder. So it is internally pressurized. It will push outside due to inner cylinder. So then you need to use the internally pressurized non-rotating cylinder equation. So you can see here, this is the tangential stress. So just substitute the values. We already know contact pressure now. Contact pressure is the thing pressurized internally. So then boundary conditions, and then you will get the general equation. If that equation valid for only this range, then you can find out the inner surface of the outer cylinder tangential stress and outer surface of the outer cylinder tangential stress. So now we already find out tangential stress due to contact pressure. That is the thing in here, due to in this contact interface. And so due to that, this outer cylinder try to expand. This is trying to because this will push this side, this will push this side. So that due to that pressure, there is a kind of stress buildup. So that stress we already calculated now, but we didn't calculate due to this given is there is already internally pressurized. So this two cylinder internally pressurized with this pressure. So you need to calculate the due to this pressure, this two cylinders stress buildup. So that stress you need to calculate. So you can see here the tangential stress due to only internal pressure. It is Pi 200 megapascal. That P naught equals 0. So tangential stress for the whole two cylinder, you can use one. So as you can assume the two cylinder as a one single cylinder and use that equation. Use this equation. You can see here C and A, because they consider this is one cylinder, this is second cylinder. this two cylinder has a one cylinder. Here to here variation is given by this equation. You can see 100 to 200 because the internally pressurized internal pressure will be applied on those two cylinders without any matter. So variation of this contact pressure we already calculate. So then at the outer surface of the outer cylinder, we already know the tangential stress now with the calculation. So substitute in B, we can get the at this point pressure stress and inner surface of inner cylinder stress. Yeah, this is the thing. Now you need to get the summation of these two because inner cylinder, this is radius, this is tangential stress due to shrink fit. This is due to contact pressure, and this is the tangential stress due to internal pressure. That pressure is 200. Due to 200 megapascal stress, this is the stress, tangential stress. This is due to contact pressure, tangential stress build up on the cylinder. Now you need to get the summation of these two. So tangential stress at the inner surface due to shrink fit, it is minus. This is plus. So you will get the some less bit between these two values, and then so you can see summations and highest value available at the contact point. You can see this is the highest value, the resultant tangential stress available at the contact surface interface. But in this case, you can see due to 200 megapascal, highest stress, tangential stress available at the inner surface of inner cylinder, inner surface of inner cylinder. So that's mean if you use one single cylinder for this particular case, the higher is tangential stress available at the inner surface, and it is also much higher rather than the compound cylinder. Compound cylinder, higher tangential stress available at the contact surface, but it is also less than the single cylinder inner surface stress. So this technique, that's why I told you we will use this technique to reduce the stress buildup inside the material. So instead using one single cylinder, we can assume this thickness is 100. So we can put this kind of compound cylinder. This is 50, this is 50. So this is much better rather than using one single cylinder. That's why we will use compound cylinder. You can see with this calculation also that is better because stress distribution is very dilute. But in here you can see the outer surface is less tangential stress, but with the when we are going to towards the center direction, radial directions, stress is very highly increased. In here it's not like that. Increase, reduce, and increase. So let's see. Tangential stress has been reduced from 333 to 285, 40% reductions. So you can see this is the variations of the inner cylinder, the outer cylinder. You can see inner cylinder stress variations due to this the maroon color one. This is due to internal pressure. You can see if it is internally pressurized, definitely higher stress available at the inner surface, and it will gradually decrease until outer surface. And due to contact, the shrink fit, due to shrinkage, you can see the inner surface. It will, because of outer cylinder, inner cylinder will be try to compress. So that is why there is a minus values, and the contact point, the inner cylinder to outer cylinder change, there is a sudden increment of the, because due to inner cylinder, outer cylinder try to pressurize internally, so it has a, positive value. So you can see the variations. So resultant one, you can see it is in between these two, and you can see internal cylinder, when you pressurize internally, first cylinder gradually decrease, and if you use if you use one single cylinder, this is the thing happen. But compound cylinder, you can see decrease and increase again at the contact point and reduce. So if you use another cylinder, it will be like this, like this. It will be like this. So if you use one single cylinder somewhere until here, what happened? It will be like this. So we can't keep the constant pressure build-up towards the radial direction. So if you want to keep the constant pressure build-up, so we need to use compound cylinder. So this is kind of simulation results. So contact pressure, yeah. So when we increase the PI, that means, so this is the variation of the resultant and only internal pressure and only shrinkage variation of the first case what we discussed, first example. Then when we change the internal pressure PI value, so you can see definitely if it is increase the internal pressure, this will goes up. This will goes up. So you can see even though it's the same level, where this value will change over, the scale is different. So the internal pressure is due to due to that due to that tangential stress goes up, but contact pressure is not going to change, because it is not the thing vary, because only change the PI. But the resultant one, it's not change that much. It is also like this. And if you change furthermore this PI value, you can see the variation. So not change the contact pressure. And if you change the contact pressure, that means delta value, so without changing the PI, internal pressure, if you change, if you don't change, so it is remain as a constant, but the increment will be increased, you can see here. And due to that, this kind of repetitive will be, that drop or increment will be increased. You can see. So that's the thing happen. That's mean if you change the internal pressure, this curve will be shift upward without changing this gap. But if you change the contact pressure or radial interference, that means the shrink fit conditions, if you change, it will change this gap. You can see. So that's the thing. So you need to understand these features very well, otherwise you can't answer the questions what they ask. So do you have any questions? I will give few seconds. If you have question, you can. So I can't see anyone raise your hand. No. So if you have any question, you can ask. No one? Okay, I will move to next slide. So there is another questions. A laminated thick wall cylinder consists of jacket shrunk into tube with A, B, C that is given. The maximum tensile stress are not exceed 140 megapascal. Then determine part A, the maximum allowable internal pressure. Part B, the initial sinkage pressure required, and part C, the assembly interface. E value is given. That's the modulus given. So consider in here when you do the calculations. So you when you do the calculation or you do the questions, you will not easily, you can see some kind of feature. So you can do the calculation even though it's a compound cylinder. Consider as a one single cylinder, do the calculation and calculate the contact point separately and get the summation. That's the thing we did with the first example. But you can do the whole thing together also. Doesn't matter, but it will be a little bit complicated. So I suggest if they specifically didn't ask to do the calculation together, you can do separately and get the resultant value. So that is a better way. So consider the combined effect of the sink width and the internal pressure acting simultaneously. So we wish to have the tangential stress in the inner cylinder at R equals A, and the tangential stress in the outer cylinder R equals B, both tension and equal to 140 megapascal. Yes, right. And consider the outer cylinder RB, tangential stress due to internal pressure is this one. Okay, so now we are not going to separately calculate. So consider whole section together. So tangential stress due to sink width, this one, sigma T2, label sigma T2, outer cylinder, and get the combination of these two. It should be equal to 140. So this is the equation. So then substitute and consider the inner cylinder R equals A. So sigma T3 due to internal pressure like this, and due to sink width, this is the equation. Now I'm not going to explain why we get this equation because you already know that. So get the summation and it should be equal to 140. And substituting A, B and B, C, then you will get the two equations. Then you can calculate the PA and P separately. You see, we don't know internal pressure, we don't know contact pressure. It's not given. And in this equation, they didn't provide the delta as well. They didn't provide delta. So you can't use first method. If you don't have delta, you need to use this method. Then delta value you can find out. Because we know contact pressure in here. So we know the equation for the contact pressure. So you can put the delta this side and P this side, and you can get the delta value. So then if they ask radial displacement or diametral displacement, you need to multiply by 2 this one. So that's about the first part of this session. But the second part also I will continue in here. So in the first part we are only considering the non-rotating cylinder. So now we are going to consider the rotating cylinder as well. So in the part 2 we will discuss the specification of thick wall cylinder, rotating cylinder. Right? And theories of failure applied to internally pressurized thick wall cylinder, lame lines, graphical technique. So it's like a, if you remember, we use a Goodman line. It is a kind of graphical representation. And if you remember, if you want to find out the inclined surface, inclined plane stresses, we have methods using, we already derived the equations, we can use that equation. And there is a graphical technique, it is a Morse circle technique. So kind of that technique, so we can find out the values, pressures, and stressors, pressures or stressors using this graphical technique. So lame lines and alternative expressions for the radial interference in compound cylinder. So those are the parts we need to discuss in this second part. Yeah, this is the general case, but in the general case earlier I show you there is another additional part with the omega, but we don't know in this level we don't know how to derive that part, but we already know that we derive this equation, these two equations for the radial stresses and tangential stresses. So these two equations, C1 and C2, then substitute in here. So if you substitute, you will get the answer for that, correct answer for this one. So C1 and C2 are constant. You already know how to find out the C1 and C2. So non-pressurized rotating cylinder, that means there is Pi and P naught equals 0 with the center hole. That means the hollow cylinder. So C1 and C2 obtained from the related boundary stresses. We already know that one in outer surface respect to it. And radial stress at the outer surface, it will be 0 because it's non-pressurized. External view internet is not pressurized. Outer surface and inner surface both will be 0. And this will be the equation for the due to rotating. So if it is non-rotating, there is no any stresses because it is non-pressurized. But the radial stresses, that equation in here, this one will and this one goes to 0 because the C1 and C2 has a P naught and Pi terms. So this will be 0, this will be 0. This is the only thing remaining, okay, with the omega. You can see this is the equations. This part we don't know how to come to this equation, but still we don't know at this level. So this is the equation. If it is required, they will provide at the exam, don't worry. So sigma t, so this is the equation. So non-pressurized rotating cylinder center hole. So then you can use that equation, and if it is Ri equals 0, this equation, Ri is equals 0, that means it is solid cylinder. Sorry, if it is equal Ri, you have values you can substitute here. It will be 0 because it is 0. We already know radial is 0. Tangential stresses, definitely it has a value. It has a value. This is for the hollow cylinder. So this is the variations. I'm not going to explain that how to draw the curves now because you already know now how to draw the curves. In here, we introduce the additional thing, the Ri, R naught multiplication, and you get the square root of that equals R. This is okay, this. Can I explain that? Keep it in mind that one. So this is R. Then the radial stress maximum value we can assume this equation. This equation, this one will be R. This will be cut off. Okay. This is R not Ri multiplication and get the square root. It is R squared then. So you will end up with this equation. So when R equals Ri, this is the maximum value, because at this inner surface it is the maximum radial stress. So tau max, so tangential stress is the value. Then what I need to explain in here, this one. So this is a rearrangement again. That particular equations, the Ri divided by R naught, and rearrange that equations. Then you can introduce the this R divided by R naught as X. Just a rearrangement. I'm not going to go through that much. This one different kind of rearrangement to use to this some calculation. This is the important thing what I want to tell you. So with this rearrangement, the ratio R to R naught ratio, that means this is the variable thing, this is the constant thing. Ri and R naught is a constant, it's a boundary condition. So it has some constant which is alpha, but this is the variable thing because R is vary, R naught, even though R naught is constant. So this is X. So in here variation is 2. So this is the variation of R naught ratio and get the relative stress magnitude. That means this is divided by the R sigma divided by sigma t. So then you can get the relative stresses. You can see the sigma t and sigma r variations. This dotted line is sigma r. This dark color, the gray color, the solid line, those are sigma t, the tangential stresses variation with the R naught ratio. That means that alpha, with the alpha variation, with the alpha vary, that tangential stress variations with the R naught ratio. That means along the radial direction, what is the variation of tangential and radial stresses. So you can see the R naught ratio. That means R equals R naught. Definitely radial stress should be equal 0. And you can see in here R equals, if it is 0, definitely radial stress will be 0 again because it will drop. And then sometimes it will drop very quickly with that ratio 0.1 with the this ratio, Ri R naught ratio. And you can see here the R naught ratio. That means if R naught equals R, you can see here in this above 0.9 because it is thin bone. So we are not going to use same theory for the thin bone. So here to here you can see the variation of the tangential stress. Maximum tangential stress available at 0.9 ratio. That means if you consider the ratio between the some specific point on the cylinder and the outer radius ratio, if it is 0.9, this is the margin point of the thick wall and thin wall. At that point you will get the maximum tangential stress. So it will a little bit reduce, but it has certain value. It is also maximum, but not that much. So this is the variation. So these are two general equations. So in Ri equals 0, that means solid cylinder. What happened? This equation Ri equals 0, this part and this part will be 0, then only remain this one. In here also these two equals 0, this is only remain. So this is the tangent radial stress then. You can see here. And sigma t, that means tangential stress, only this one. And R equals Ri. You can simplify this much. R equals R naught, this one. So this is boundary condition apply on the equation. So you can see the variation of the solid cylinder. So this is not a hollow cylinder. That's why the radial stress available at the center as well. So at this point, radial stress and tangential stress both are equal. And this surface, outer surface. So you can see the variations with this curve. So this is the thing what I want to explain. Non-solid rotating cylinder, that means hollow cylinder. So this is the equation. We already derived this equation. Tangential stress. This is the equation. If you remember, this is the equation. Okay, so non-pressurized rotating cylinder. So from that you can get this one. And solid rotating cylinder, you can see the with the calculation you can see this there is 8. Okay. So then this is 2 times. If you have the hole inside this, even though there is a small hole, stress will be 2 times. So not 2 times, 8, 4 times, 2 times, yeah, 2 times. So this is the thing. So this is we discuss is the stress conservation. You need to use SI unit and everything. About unit and density, if you use kilograms per cubic meter or grams per cubic centimeter, something like that. Up to that, if you use grams and centimeter, you need to use grams and centimeter like that. So you need to consider. Until that point, do you have any questions? Rotating cylinder, you don't want to worry too much because it's not difficult. It just equation will be provided definitely because you don't know how to derive that equation. So you need to know what are the parameters available there. So just substitute and get the answer. But rough idea you should have. That's all. So any questions? Are you there?
Yes, sir.
Any questions for me?
No, sir. Not so far understood.
Okay. There is a steel rim. Internal diameter and outer diameter is given. Shrunk onto a solid cast steel wheel. So diagram will be provided next slide. Outer diameter 500 millimeter. Assume thickness to be uniform throughout. The pitch between members should be such that there is a diametral interference 0.15 millimeter. Then when you consider the interference, you need to divide by 2 this way. At the design always peak conditions of 8000 RPM. So this is rotating cylinder. For both materials, E and nu is given the same, density also given, but diameter intensity is required at 0 RPM. So the operating stresses existing in the rim and wheel. There is a kind of assumption that both rim and wheel both are made by same material. For the calculation, you can use that as the same material, otherwise it will be complicated. That's why. Sorry, diagram is not available. Okay, so can we imagine the lecture note? I don't know the there's diagram or not. So this is kind of this kind. I will go rim and wheel like this. Rim doesn't have the inner radius, so rim. This is wheel. This is 500 outer diameter. This is inner diameter of the steel rim and outer diameter. So this kind of compound cylinder. So stress due to rotation. So rotation also produces stress. So we can consider the two cylinder as one cylinder. I told you. So the rotating affect to both cylinder same way. So you don't want to calculate the separately the stress due to rotating. So you can calculate general equation for both cylinder as a single cylinder, and if you want, you can separate later. So consider two cylinders separately. It is also can be big, but it will be little bit lengthy. Then your answer will be little bit lengthy. And stress due to interference, stress due to rotation separately calculate, and stress due to interference. At that time, you need to consider this thing separately, definitely to the contact, because you need to consider that equation with the delta equation, contact pressure equations separately for the both cylinders. So if two cylinders are considered separately, when finding the stress due to rotation, find the interference at the operating RPM and use this interference to find the stress due to interference. If two cylinders considered as a one cylinder, then find the stress due to rotation. Use the static interference at 0 RPM to find the stress due to interference. So you will consider the if it is one cylinder, there is no interference. That's the meaning of that. So then you will consider it is 0 RPM, something like that. You need to calculate the 0 RPM static interference for the interference, and then convert to the RPM value. So let's see, when we do the calculation, you can easily grab that. For the solid cast steel wheel, the inner cylinder stress due to rotation is this equation. So for the rotation, radial stress, the equations you can see in here, the other they substitute all the given values and get the general equation. If you want to find out any radial stress, you can just substitute the radius and get the value for the radial stress. Okay. Then tangential one, same way, only they consider rotating part. Yes. Then get the general equation. Then at the inner radius. Then now we are going to substitute R value. R equals Ri. So this is the value. Tangential one also same. Same answer. Then outer radius, it is equal to 0. When you substitute, you can see it is. So we will use these two equations. So R0 and Ri is provided already. So you substitute and get the values. And just need to calculate the radial deflection. You are at. I told you we call the U as displacement of the radial displacement. So you are at the outer radius. This equation you already derived. This equation we already know. So just substitute that equation and find out the tangential strain epsilon t If you know that, if you know the radius, then you can calculate the radial deflections. For the steel rim, the outer cylinder is restricted rotation. Earlier we did the inner cylinder, now outer cylinder. This is the general equation. This is for the tangential one. Now substitute in the boundary condition, inner one and outer one, to that two equation. Now we need next to calculate the radial deflection. You are at inner radius. So this is the equation. We know all the parameters. We already find out inner radius, those value, sigma r and sigma t. Use and calculate the URBC. We know the sigma t in here. To find out the UR. We use this theory for the inner cylinder, outer surface, outer radius, outer cylinder, inner radius. Okay. Then at 8,000 RPM, the radial interference will be decreased by this difference, because we already calculated that, this value and this value. So in here, this is the inner cylinder, outer surface. Next one, outer cylinder, inner surface. So that deflection variation, I mean difference between that deflection displacement should be equal to the radial interference. That is at 8,000 RPM. Due to rotations, this is the deflection at the interference. Since at 8,000 RPM, the diametral interference is this much. So in here, you already find out the radial interference. So you need to get the summation of these two, get the total diametral interference. But you need to multiply by 2 this one, because this is radial interference. So you multiply by 2. This is the radial interference due to contact pressure. This is radial interference due to rotation. So if you want to, this is not radial, this is diametral interference. So this is radial interference due to rotation. So if you multiply by 2, you will get diametral interference due to rotation. So total diametral interference is the summation of these two. It is 1.01 millimeter. So as I told you, if you want to find out the radial interference, you need to divide by 2. It is 0.075 millimeter. The interference pressure will be given by this equation. We know that the equations and we know delta, so we can find out the contact pressure. So for the solid cast steel, the inner cylinder stress due to interference is this is, we already know, because at the contact point, the tangential and radial stress should be equal to that contact pressure, the minus value. So outer cylinder, it is due to interference is, you need to simplify that equation first, then substitute and find out the tangential and radial stresses for the boundary conditions. We already know that boundary, this value, it is already find out because it cannot be changed. This is the inner surface of the tangential one, outer radius of the outer cylinder, it is 0. And then if you assume that no yielding occur and no separation of, that means the two cylinder touch always. Otherwise, if it is if there is any gap, there we call this a separation. So there is no separation. So keep in mind those assumptions. Sometimes you should make at the equations. So no yielding, no separation of the material surface of at 8000 rpm, because when it's rotate, the two cylinder, if there is compound cylinder, assume there is two cylinders together, so when it's rotate, the expansion of the cylinders due to rotation can be difference. Due to that, there can be some tolerance between the gap. So we assume there is no separation. For an example, if you have two metals, if you heat up those two, if you use some glue and make the bimetal, and if you heat up the one, out of these two, one type of metal can be expand much more rather than other one. Then that bimetal can be separate to bend to other side like that. So separation can be happen due to rotation. So we need to consider that separation not happen and no yielding, no yielding at that contact point due to that rotation. So those are two assumptions. The melting surface occurred 8000 rpm. The stress due to the rotation can be calculated as the assembly was a solid wheel of 275 millimeter radius. Because to remember the question, the calculations you can do that. I didn't remember the radius values provided. You need to go to in here. This is 550. That means if you get the average value is 275. So midpoint of the cylinder. So
Sir, why do we take the midpoint?
Midpoint due to this can be calculated as assembly was solid wheel. Because the second method, what is the condition? There is a two method. We can consider the two cylinder. Yeah, two cylinder consider one cylinder. So when we consider the one cylinder, we assume there is no any. We calculate using without non-rotating cylinder as a non-rotating cylinder, and then introduce the rotating part separately. In here, this statement they made, I think. Let's see. They just put that statement. I think it's don't worry about that. If you assume no yielding, no separation at the metal surface of at 8000 rpm, the stress due to rotation can be calculated as if the assembly was a solid wheel of. I think when we do the calculation, we can see that. I think this because we didn't do the calculation in here, so assume this is a rim. Okay, this is the wheel. So these are rim and wheel touch each other due to expansion. This tire will, okay, I will draw here. This tire will be like this, okay, and rim will be remaining here. So there is a gap. Okay. So if it should be, definitely should be without gap, no. So then rim also will be expand to until this point. So with this calculation, you can see this outer cylinder inner surface will be expand until this point. That means if you consider the one single cylinder, the rim and tire, rim and wheel, so that tire will be expand to until this point due to rotation. Did you understand what I was explaining?
Yes, sir.
So keeping the touch between these two, the inner cylinder also should be expand to until that point. So with the calculation, you can see the expansion, and the rim also should be expand to that much length.
Okay, sir.
So, because I know I'm not going to continue to touch with the values, no. So if I touch with the correctly value with the values, we can see the this value and link between this value and our answer.
Okay, sir.
So what you can try out. If you have any question, you can contact me.
Okay, sir.
Okay, second method, we calculate the stress due to rotation. The main difference between these two, consider the as a one single cylinder. Second method, first method or second method considers two cylinder as a one cylinder. Or other method is consider the two cylinders separately. So that is the main two method. Don't worry, equations are not going to change. The analysis method will only change. If you analyze separately, you will get the summation separately and get the summation. If you consider one single cylinder, then you need to introduce the contact pressure later, because you didn't apply the contact pressure. So that is the main difference. Method 2 I'm not going to in detail explain in here. So just so anyway you will get the same answer. So I will skip that part.
So which method should we go by? Like which one is easier to
It's up to
compute?
the question. That's a problem. So you need
like
to
for
take
this question.
these questions. I think you can use separately and get the summation. That's the better.
Okay.
Because that's one better, but in here also first method they use a separate method because they calculate the expansion of that displacement separately. At that time, there was a trouble because when you consider the expansion of that due to rotation and pressures, there will be displacement. But if you consider two cylinders separately, what happened? One cylinder can be expand. The one outer cylinder inner surface can be expand much higher rather than inner cylinder outer surface. Then there is a gap. So you need to keep in mind that gap. That gap should be equal 0. So that's why they mention in here that particular statement very clearly. This statement. If you consider separately these two cylinders, you need to make sure this touch, because if you apply the theories to this cylinder separately and this cylinder separately, this gap will be forgot. I mean, it will be missed. So that's why you need to keep in touch these two without gap. But when you consider the one single solid cylinder, we don't want to worry about this gap. We assume one single solid cylinder. So in this case, if you apply the theory separately to do the two cylinder, keep in mind you need to focus on this gap. Okay, and if there is any gap, your calculation is going to wrong. But if you are considered the one single solid cylinder, you don't go to the gap. At that sense, it is easy. Are we clear?
Yes, sir.
So if you are okay with keep in touch with the gap, keep in touch with, you need to always check the gap. Okay. So I will skip this method too. You can try. If you have any question, you can ask. I'm available anytime. You can. Okay, if you are doing the calculation, you can send me and I will check it. So these are the variation of the stressors calculation with the rotation and the pressures. Check it. So I will move to the next title, otherwise it will take long time. Is it okay? So I don't think you will get that much of lengthy questions at the exam. Okay, so this question will get exactly you need to, at the exam you need to understand the questions and you need to answer the questions. Maybe you will get the 45 or 50 minutes for this kind of questions. So so your whole paper 2 hours and there's 4 questions. Am I right? 4 questions. Yeah, 4 questions. So you have 30 minutes. So when you wrap to these sessions to 2 hour paper, you will not get this kind of lengthy question, but they can ask one part of this kind of question, definitely. Not this kind of lengthy question. Are we clear?
Okay, sir.
Theories of failure apply to the internal pressurized thick wall cylinder. Again, normally failure will be happen at the inner surface, as I told you earlier, and it is also happen due to tangential stress. So you already show the product graph and the values also. The maximum stress as a magnitude is available for the tangential stresses at the inner surface of the cylinder. So normally it will fail as a yield failure. So what pressure is required to just initiate the yielding of the internal surface of the cylinder? So what is your suggestion? Any idea? So if you remember, we know what are the failure theories. So we discussed 5 methods calculate the failure theories. If you remember, Tresca theory, von Mises theory, maximum principal stress theory, maximum principal strain theory, distortion energy theory. So kind of different kind of theories. So in here also that's it's up to the application and method, which method you are going to use. So if you remember, if you use Tresca theory, that means shear stress theory, you will get the maximum stress allowable on the system, and if you use von Mises theory, if you get the ready for the maximum stress allowable, those are two different. If you remember the curves and other things also, so you can see the first quadrant. Sometime the principal stress and shear strain theories are match each other, but when we are going to second quadrant, it is different. We plot the curves and other thing also. So if you remember, so it's up to the mechanism we are going to use, or method you are going to use. Longitudinal stresses mean I draw the, okay, assume this is the segment we use from the cylinder. This is radial stress. This is tangential one. Longitudinal mean out of the surface. So not this. Yes. Z-axis. This is x, right? Z-axis is the longitudinal direction. Length direction. That is a longitudinal direction. So in here we assume there is no sigma z. That means no longitudinal stress. So in here only biaxial. Then sigma r and sigma t only. So then we can calculate the using that equations. If it is a R, we know if it is internally pressurized radial stresses. We already calculated these things using equation. It's minus pi, radial one like this, and then so you can introduce the yield strength of material, and in here, even though this is pi, this is much higher than pi. You can see this is 1. Definitely there is a pi, then 1 plus this one part also. Even though this is divided by some value, this ratio never going to be I mean much larger value, no? It will be in between 1 and 0. So then this one minus p, I mean radial stress and tangential stresses has a difference, but it is larger than this value as well. So you can see here, so this ratio, if it is 3 upon 2, that means 0.6, ratio between these two is 0.6. So then you will get the radial stress at the inner surface is a minus pi, so that is internal pressure, that's why. And then the tangential stress at the inner surface, it is 2.6 pi. That means 2.6 times of this radial stress. Definitely we know tangential stress is much higher than radial stress. We already do some example, and I explained already, so we know. But it is 2.6 times. If you know this ratio, Ri R naught ratio, if you know, is 2.6 pi. Then if there is no shear, and no sigma is it, that means like longitudinal. So then you can use maximum principal stress theory. So in the maximum principal stress theory, that the values comparing these two values, this is the value you need to take care, because this is every time less than sigma t. Tangential stress is the thing you need to consider failure analysis, not the radial stress. Radial stress never going to be much higher than tangential stress. Tangential stress, so you need to consider tangential stress and yield strength. So if tangential stress, if it is equal to the yield strength, then definitely failure will be happen. If tangential stress not equal to the yield strength, you don't want to worry about the radial stress, because it is less than tangential stress. So that's why we are considering the tangential stress and yield strength. So if it is equal to the yield strength, that means in this case the ratio is given. So R naught ratio, it is 0.6. So then the sigma t value is this one. So if that value equal to the sigma y, that means strength, you can draw this is the fourth quadrant, because sigma y value is a compressive load, that's why. So if you remember, we can draw the experimental theory. This is the safe zone. This is the failure zone. So this is the fourth quadrant. So this is safe zone. This is the failure zone. So this is sigma t, like sigma x. This is sigma y, like sigma y. So then if yield strength, sigma t, if it is less than yield strength, it will be inside. Definitely sigma r is less than yield strength because it is sigma t is higher than sigma r. So we will get the coordinate somewhere here if it is safe, like this. These are the coordinates. So this is just kind of a relationship between the PI and yield strength. You don't worry because PI and they put the 2.6 this side. So 1 upon 2.6 will be give this value. So you can reach the maximum value for the PI from if you know the yield strength. Assume you have yield strength as 1,000 yield strength, then you can only apply on this cylinder as an internal pressure 385. So with this relationship, you can easily, if you apply internal pressure 385, that material will be somewhere here, that cylinder, inner surface somewhere here. So if we apply 386 megapascal pressure, that particular material will be fair. So I hope you understand that one. So then Tresca theory, maximum shear stress theory. So in that theory, there should be a shear stress maximum point you need to consider. So you need to draw the Morse circle, or you can use the equation if you want, but tau max will be given by because we already know the principal stresses, two principal stresses, because at that plane there is no shear. Then you need to get the difference between 2 and divide by 2. This relationship I already explained. Okay. If you know the principal stresses, sigma 1 and sigma 2, sigma r and sigma t like principal stresses. So sigma 1 and sigma 2 difference divided by 2 given by those relationships given by tau max. So if you get the difference these two and divide by 2 is the radius of this circle. So radius of this Morse circle is tau max. So you can convert now, get the relationship with the tau max and the yield strength. So normally nominal stress and shear stress relationship, I already explained these things. So tau equals 0.5 nominal stress. This relationship I already explained at the first lecture, if you remember, first or second lecture. So we derive this equation as well with you. So then this is the tau max, and this is apply. We already derived 45-degree as well. Angle between these two principal plane and maximum shear stress plane. Those two planes angle between those two plane angle 45-degree. We already derived these things. Okay. So this is the maximum shear, yield strength divided by 2, and we know already at that time changes in stress. It is like a sigma 1. This is like a sigma 2. It is minus p. Just substituting that one. Then pi. So we will get the pi values of pi from this side, and simplify that equation until this point. Then you will get the this kind of relationship with the internal pressure and yield strength. So then you can see, even though here pi you can reach to the 385. The yield strength, even though 1000, this is you can only reach with this method 278. If you use maximum shear stress theory, you will get the safe zone until 278 megapascal. Okay, so that's why I told you. That there is a difference between the method you are going to use given the safe zone different way. So the maximum distortion energy theory, von Mises theory. So that in that theory, hope you remember that there will be like a parabolic. I mean, this kind of oval shape boundary line. So this is the equation of that ellipse. So this is the equivalent stress for the two principal stresses. This is like a sigma 1 and sigma 2 again. Sigma 1 is squared plus sigma 2 is squared minus sigma 1 sigma 2. So sigma 1 sigma 4 sigma 1 is maximum principal stress, this is the minimum principal stress. Just substitute and you will get the yield strength relationship with the yield strength and pi like this. You need to get the square root value. Then it is 0.311 sigma y. That means if sigma y is, if it is 1000, it can reach only maximum, as a maximum value is 311. So the maximum allowable pressure can be varied with the theory which we use. Yeah, so this is the relation. I mean, comparing the technique, so different technique, different relationship. This is again remind the theory what we discussed, non-rotating cylinder. This is the two equations we will use. Non-pressurized rotating cylinder, this is the equation. There is only omega terms. Then this equation you need to keep in mind. And Lehm's graph. So this graph, I hope you remember this equation now because the lengthy session. Sometimes you will forget. So these two equations, you can see these are constant. We already discussed. So you can draw this line as a y equals mx type. So if it is non-rotating, this is like a if you consider r is 1 upon r squared as x. So this is like a 1 y equals mx plus c type equation. This is also. So this one and this one is same, and this one and this one is same. Only difference is plus and minus. So then, yeah, as I told you, we can plot the curve against stress versus 1 upon r. So then you will get this kind of line, two lines. So this is if you get the mirror image of this line, slopes are same, slopes are there. If you get the slope value same, b, this is minus b. Only magnitude is same, sign is changed. So if you get the mirror image of this slope b, you will get the same line this side. It is the extension of this line. So if you, I don't think in the lecture slide is available, but you can see lecture note. It is same thing, but then if you are going to using Lehm's line, if you got the minus side of the 1 upon r squared, it will provide the sigma t values, but you need to change the sign. Sign means not sign. You need to consider sigma t, and if you are going to positive 1 upon r side, it will give the sigma r. That is the main technique in here. Same equation you can use. You don't want to calculate against sigma t, but you need to, if you know the r 1 upon r, so get the 1 upon r sigma r value. That means radial stress. The same, okay, like this I will show you. So assume 1 upon r value 0.5. So then you will get the sigma r at that time and sigma t. And sometimes you don't want to plot this curve, you can extend this line and you can get the reading for the y coordinate for the minus 0.5. It will give the sigma t. So you don't want to waste time for the plot this curve. Important of this lens technique, you can calculate, normally if you have the equation, you need to substitute that equation and find out the sigma t and sigma r. So this graphical method, you don't want to substitute to any equation. If you, after you plot the curve, so at any r values, you can easily read the coordinate as a y coordinate. You can easily read the stress value. That is a main advantage of graphical method. So lane technique means we will use these two equations and draw the curves belong to this sigma and sigma t, and we saw the relationship there. Then using one line, we can read the both tangential and radial stresses. So I already explained this thing. Yeah, it's available here. Mirror image. So I already explained this one as well. Swing fit. So these are the equations. So the equations, compound cylinders, how we can apply. So that's all about the session. So if you have any question, you can ask. So do you have any questions? Shinal, for me,
No, sir.
did you understand it? I don't believe. Because these sessions normally I will take, even though this is planned to 2 days, I need to at least 2.5. Again, that's been 5 hours at least I need to explain this one. So otherwise I can't explain very clearly, I know, but I try my best to do that in here. So Udara,
Yes, sir.
do you have any questions?
Not at the moment, sir.
Not at the moment. After the exam, don't ask the question. Then no point to ask the question. So anyway, that's about the lecture. So need I do the tutorial? Discuss the tutorial with you? So same kind of questions. I mean, with the examples. I think this is nothing else, just substituting the equations and find out the stresses and plot the curve, isn't it? Just you need to find out which one is internal pressure, which one is under external pressure, then simplify the equation. So if it is internal pressure, non-rotating, simplify equation and substitute. But when you substitute, keep in mind sometime inner cylinder outer radius, the next cylinder, it can be the inner radius. So I think you understand what I mean. So same radius, for some cylinder it can be outer radius. Another cylinder, it can be the inner radius. So when you substitute, you need to keep in mind those things. Switch according to that, relevant to the questions. Otherwise, because R naught you will consider 50 millimeter for another cylinder. Same R value you need to use outer cylinder, it is inner radius. So sometimes it will forget. I saw when I mark the papers sometimes. So that is some of the problem, some of the persons, because at the exam you are under pressure, so you will forget to switch those things. So as I told you, you need to derive the general equation for this, and then you can find out the at any point stresses. You can sigma T and sigma R generally for the specifically that case, particular case. For the question, this is general case. So you can find out any point of the cylinder stresses. So question would be different condition and find out thing. In here, delta is provided, so you need to find out the contact pressure first. So if you know the contact pressure, you can find out the sigma R and sigma T using that contact pressure. You can see.
Sir, excuse me.
Yeah.
You haven't shared any screen.
Oh my God! Why don't you?
Now only got to know that you're talking about the tutorial.
Okay, no one told me. Because I. Seriously. So, so I browse here and show this everything, but you didn't see anything. Oh my God. Anyway, yeah, okay. This PDF I discussed until this point. Okay, in here, so I'm talking about this sync fit. So you need to find out the contact pressure using that equation. Delta is given. Then that contact, due to that contact pressure, internal cylinder will be externally pressurized, and outer cylinder will be internally pressurized. So you need to use that two equation for the calculate the sigma T and sigma R from contact pressure. Then separately calculate the due to internal, there is a internal pressure. There is internal pressure. Due to internal pressure through the radial direction, sigma R and sigma T variation. So it is given by here. So you don't want to calculate separately. You can use and get the summation of these two later. So this is the example what we discussed, a similar example. That's why I'm telling. So you don't want to again as a number. I will just summarize what we did, what they did in here. Get the idea about that, and but you need you don't do that yourself. Okay, you need to all of you need to do the calculation yourself. So you also going to review like this, you are in trouble. Okay, so you need to identify how to, sometime when you do the calculation in here, you don't know how to simplify that equation to use. Okay, so this one you need to simplify until this point. So if you do the wrong way, no point to discuss somewhere here. Okay, so better you need to do the calculation yourself and check with these answers. If there are any wrong calculation or mistakenly did something, or if you don't understand it, you can contact me.
So if we are to contact you, how can we contact you? Through mail or how is it?
Don't you have my mobile number? Really? I thought you all of you
No,
have
sir.
this. Okay, you can email me if you want. Then if it is a big issue, I can okay, like this I can arrange Zoom session individually.
Okay.
Or else You can call me. I will give you my mobile number. Doesn't matter. I think Akhil have my mobile number.
Okay, I'll get it from him then.
And Shinal, I think you also have, no? Isn't it?
No, sir, I don't.
Akhil and your batch, who said it? Eranga, isn't it?
Wrong.
He also have mobile number, and the junior batch also have my mobile number. So
Tihan might have.
I'm not going to tell here. Okay. If you want, you can email me. I will put the email with my mobile number. It is not a secret, but I don't want to tell it here because I will publish this one. Then,
Yeah, okay.
So that's the you need. So this last question, third one, they didn't provide the delta. You need to find out delta. So you can see at that time you need to do the separate way, not like this. So you need to identify the question. Then you need to apply the method you are going to use. Is it clear? I mean, I know it's not totally clear, but it's manageable now, no? Oh,
Yes, sir.
Udara?
Yes, sir.
Yeah, clear then?
Manageable. Okay, sir. We'll try a question and we'll get back to you if there's any problem.
Okay.